Okay, welcome to Chapter 6, Lecture 6 for working now on quantifiers and definite descriptions. We've been looking so far at very simple forms of propositions made up of predicates and names. Things like Mary laughs, which translates as the predicate logic laugh applied to the predicate logic name Mary, which denotes true if and only if Mary is a member of the set of individuals who laugh. I write if and only if as IFF, and I will be using that here in this talk as well as in the textbook from here on. So formally, we end up with something like the translation of Mary laughs ends up as laugh of Mary. And for the denotation, I'm going to introduce this new new way of indicating it. It's going to be in interpretation brackets that tell us how to interpret the predicate logic formula laugh of Mary. Okay, so it's doing a very similar thing to what the double bars are doing up there. This is taking something from the language of predicate logic and giving us a denotation. Okay. Okay, so the next question, what about expressions like everyone, someone, and no one? Can we treat these the same way that we treat the name Mary? They certainly show up in the same places. You can say everyone laughs, someone laughs, no one laughs. Basically anywhere that a name can go, these expressions can go as well. However, it turns out that we cannot actually analyze them in the same way. In particular, we cannot analyze these expressions as picking out individuals. And I'm going to go through that answer, why not, in some detail. I'll look at each of the three quantifiers, this is what we call them, quantifier expressions one by one, and show that each one has its own problem if you try to analyze it as a name. Okay, so suppose that no one actually was a name. That means that it translates as a symbol of some sort in predicate logic. And that predicate logic symbol denotes some individual n. Okay, that's what it means to be a name. Then no one laughs would be translated as laugh of n. And that would be true if and only if the denotation of n is in the denotation of laugh, which is true if and only if the individual denoted here, n, is a member of the set of individuals who laugh. Okay, that's what the analysis would have to look like if no one were a name. But then we would have to ask the question, who is n? N can't be Mary. If Mary laughs, then the sentence no one laughs is false, not true. And for that same reason, n cannot be John, Bill, or Sue, or any other person. So if we're going to use something like n, it would have to be some non-existent individual, maybe an individual that not only doesn't exist, but somehow couldn't exist. I don't know. But even if we do that, we still can't use, we cannot analyze no one as a name denoting any weird individual like that. Here's why. For any name n in predicate logic, laugh of n is true if and only if the denotation of n is in the denotation of laugh. The denotation of laugh is a set. It contains all those individuals who laugh, and it doesn't contain any individuals who don't laugh, but it's just a set. It could be a set containing A, B, C, D, who knows who, okay? Then for any two names that have different denotations, M and N, for example, whether laugh of M is true is completely independent of whether laugh of N is true. They could both be true, they could both be false, or either one of them could be true while the other is false. all of those possibilities exist, and knowing that one of them is true then tells you nothing about whether the other one is true. But with the sentence, no one laughs, that's not the way it works. If we know that no one laughs is true, we know that Mary laughs is false. Those two have dependent denotations. The first one can only be true if the second is false. Now, they can both be false, that's true, okay. But they cannot both be true. And so there is a dependence between them. And that means that no one cannot be translated as a name. Now, we started off with a supposition. Suppose that no one is translated as a name. We've come to a conclusion that can't be sustained. Namely, that if no one is a name, it should be possible for no one laughed to be true, and for Mary laughed to also be true. But we observe that that's not possible. So we have to conclude that our original supposition was wrong. No one cannot be a name. Okay, we can come to the same conclusion with someone. The situation, suppose that John laughs and Mary does not. Okay? Then we observe that the following two sentences are both true. Someone laughs and someone does not laugh. If someone were a name, this shouldn't be possible. If someone were a name, it would be like Mary. Mary is a name. And if you say Mary laughs and Mary does not laugh, those can't both be true. One of them is true, the other one is false. And someone should behave the same way. Here's why. Because if someone is a name, its translation is as some symbol S, which is a name of predicate logic, where the denotation of S is some individual, italicized S, where that italicized S is an individual, okay? Then someone laughs translates as laugh of S, and laugh of S is true if and only if that italicized S is a member of the set of all things that laugh. Someone does not laugh ends up as true if it's not the case that laugh of S. That is, it translates into tilde, that's our negation of laugh of S. And that ends up as true if and only if laugh of S is false. Yeah, I'm getting there. Right? And laugh of S is false is going to be true just in case the individual denoted by the someone is not a member of the interpretation, the denotation of laugh. However, it's not possible for both of these to be true. Nothing can both be and not be a member of any set. That includes whatever our denotation is for someone. Our conclusion, someone cannot be analyzed as a name. That is, our original supposition that someone was a name cannot be kept. Okay, continuing on our long answer to whether these expressions can be interpreted as names, we look at everyone. Consider the following situation. John is 90 centimeters tall. Mary is 150 centimeters tall. And Pat is 210 centimeters tall. And we're going to consider sentences of the following form, where you put some name in place of an X. X is over 1 meter tall, or X is under 2 meters tall, or both. Now, it should be obvious, especially if you add the or both to make it very clear, that this this is going to be true no matter who you put in place of X. Pat is over 1 meter tall, or Pat is under 2 meters tall, or both. That's true, because Pat is over 1 meter tall. Pat's not under 2 meters tall, okay, so not both either. But no matter who you put in there, the sentence is going to come out as true, okay? But if you put the word everyone in there, it doesn't come out true. Everyone is over 1 meter tall, or everyone is under 1 meter tall, or both. Well, in the situation we just described, that sentence is false. Right? 2 people are over 1 meter tall, but not all 3. 2 of them are under 2 meters tall, but not all 3. And it's not the case that everybody satisfies both of those. There's only one person who is both over 1 meter tall and under 2 meters tall, not all 3. Okay, but if everyone were interpreted as a name, it should not be possible for the sentence to be false. Conclusion, everyone cannot be interpreted as a name. So as I mentioned at the beginning, everyone, someone, and no one are called quantifiers. And as we've just seen, quantifiers are not names. That is, their semantic type is not type E. So this gives us 3 very clear, immediate questions. First off, what is their semantic type? Second, what is their logical translation? And third, what do they denote? Well, we'll start with the type. We have the following type information. We know that these 3 sentences, everyone laughs, someone laughs, no one laughs, are all 3 things that can be true or false. So the sentences themselves are of type T. Furthermore, we have been assuming all along that laughs is a one-place predicate. This type is ET. So if everyone is not of type E, same with someone and no one, then what type can it be? Well, the answer is there's only one other type left. It's the type ETT. This is a type that takes an ET expression as its argument. And here, laughs is an ET expression. It gives back something of type T. Our sentence is of type T. So the types match up. So supposing that our everyone, someone, and no one are all ETT type expressions. Next, what do they denote? How do they get translated? And we're going to start with the following basic intuition. This is one of 2 intuitions that people use for everyone. The other one will be saved for a different chapter that we will not be doing in this class. The basic idea is this. To see if everyone laughs is true, I'm missing a word, check. Check 2 things for every individual. First, is that individual a person? And second, does that individual laugh? The sentence everyone laughs is going to be true if and only if there is no case in which 1 is answered yes, the individual is a person, and 2 is answered no, that individual doesn't laugh. All other pairings of answers are fine. So let's step through this with a particular situation. Suppose we have 5 individuals, A, B, C, D, and E. A and B are people, C and D are monkeys, E is a pencil. A, B, and C laugh, D and E do not. Okay, intuitively in this situation, everyone laughs is true. This approach predicts that fact. Why? Well, let's take a look. We check for each of individuals A, B, C, D, and E, we have two questions. Is that individual a person? And does that individual laugh? And here I've gone ahead and set out the answers for each of these individuals. For individual A, person, yes. Laugh, yes. What about B? Also a person, also laughs. C is not a person, C is a monkey, remember. But C was a laughing monkey, so C does laugh. D was a very serious monkey, not a person, doesn't laugh. And E was a pencil, not a person, doesn't laugh. Right? So here, no individual gives us the pattern yes for the person question and no for the laugh question. And so everyone laughs is predicted to be true. That's a correct prediction, so this is good. Now, how do we get this result formally? We're going to get it by taking the sentence, everyone laughs, to translate as this formula. This formula that I am having a really hard time highlighting. There we go, this formula. We read this for all Z. If Z is a person, then Z laughs. Okay. But in order to check whether this sentence is true or false, we have to know how to interpret this predicate logic formula. That is, what is the denotation of this formula? Well, it's supposed to be the denotation of the sentence, and the sentence is supposed to be either true or false. So we know that it's going to give us something true or false. And what we're going to do is give a way of interpreting things of this form. Something that has this universal quantifier, we call it, for all Z in the front, and some kind of an expression inside of parentheses there. And we're going to say it's true if and only if something or other is the case. Okay? Now, this is a fairly long and complicated process to spell out in detail. So we can't really just fill in those dots very simply. Before we can do that, we have to know what to do with this Z here and this Z here. Those are called variables, and interpreting them is going to be the first order of business. Step one, interpret variables. A variable does not have a fixed denotation. Its denotation varies, and that's why it's called variable. You can think of it as acting as a placeholder for individuals. What we need is an analysis that associates a variable with an individual in a way that's flexible. So we're going to do this. We are going to add instructions for what to do whenever we meet a variable. This is what our instructions are going to look like. X/Z. And the meaning of the instructions is going to be this. Interpret the logical variable Z as the individual X. Okay? So the Z is part of our predicate logic. It's one of the things that we had showing up in our formula. The X is not. The X is part of our denotations. It's one of the individuals of our set theory. Okay? So the instruction says take the logical variable and assign to it as its interpretation the individual X. And we're going to take those instructions and we're going to put them here. We're going to attach them to the right interpretation bracket. And so we're going to get things like this. This is the denotation of Z with respect to the instructions that tell us to assign to Z the individual X. So for any individual X, this, we can call it the denotation of Z with respect to the instruction to assign Z to X, denotes X. For example, suppose that we put in place of X, M. M could be Mary. Then this ends up denoting Mary. Suppose instead we gave it John as our value of X. Okay, then this is going to denote John. The only thing that we can't do is leave the variable without instructions. This is not Mary, it's not John, and it's not anybody else. And it's not everybody else. It simply is not defined. So we're going to use this as our way of flexibly giving an individual as our denotation for a variable. It's flexible because if you change the instructions, you change the denotation. Okay, the instructions X for Z only affect the interpretation of Z. But we can add the instructions anywhere we want. If we add it to something that does not contain a variable, it's not going to have any effect. So for example, we can think of this as the denotation of the name Mary, where any occurrence of Z is interpreted as X. Well, there is no occurrence of Z. So the instructions are kind of empty. They do no work. They can be ignored. We still get the same thing that we got before, which can be written like this. It's Mary prime. It could be written as M, which I've been using elsewhere for the individual Mary. And the same is true for laugh. This gives us the denotation of laugh, where any occurrence of Z is taken to denote individual X. And laugh, that's a predicate. It doesn't contain a Z, it's just laugh. And so the instructions again tell us nothing. We can ignore them. And we can do the same thing with laugh of Mary, but this is where we're going to start to see the importance of this particular fact. When we interpret a complex expression, like laugh of Mary, that's made up of a predicate and an argument in this case, we've always related it to the denotations of the parts. But this time, we don't just have a standard denotation, we've got this X for Z tagging along, telling us what to do in case we come upon a variable Z in particular. And we want to carry that instruction along with us so that it shows up here when we try to interpret Mary, and here when we try to interpret laugh. And we'll see why in a minute. So anytime we have this instruction for a complicated thing that we're breaking into pieces, we carry that instruction along to the pieces. This is the interpretation of Mary following those instructions. That has to be a member of the interpretation of laugh following those instructions. And as we saw, the instructions make no difference in this case. It's true just in case Mary, the individual, is a member of the set of individuals who laugh. Okay. So now what happens when we do have a variable inside of that expression? Here we have the expression laugh of z. I've changed Mary, the name Mary, into the variable z. Well, we're interpreting this with respect to some individual x. Whatever individual that is, this is going to be true if z, the interpretation of z with respect to that instructions to interpret z as that individual, is a member of the interpretation of laugh following the same instructions. And this time, those instructions matter because here they tell us to assign to z the individual x. So laugh of z with respect to the instructions to interpret z as x will be true if and only if x is a member of the set of individuals who laugh. Okay. So this is where we see the importance of the fact that the instructions added to the large full proposition, laugh of z, are also used for interpreting the pieces that make up that proposition. Okay, the next thing we need is to give what we set out to give, an interpretation for expressions of this form. Expressions that have this upside down AZ, which we read as for all Z, applied to some formula. Here I've used the Greek symbol phi. Okay. And here's why, where the instructions for variables comes into play. Okay, so now we're going to say this. The interpretation of this formula for all z phi, its denotation is true if and only if for every individual x, the denotation of phi is true following the instructions to take z and interpret it as x. Now, we don't know where the z is going to show up, and this is why we want to carry those instructions down into every piece that we look at inside of phi. But this is the general form. Okay. Here, the original does not have any instructions. It could, but it could not. The instructions are not needed for that interpretation. The instructions are absolutely crucial, absolutely essential here. So our goal is to give an interpretation to an expression of this form. For all z, if z is a person, then z laughs is going to equal, and it's going to be true if and only if something. But we have inside of there this arrow, and we need to figure out how to interpret that arrow. In chapter 2, we we looked at that arrow about how we could interpret it. We decided it could be given a truth table. But here, a truth table isn't going to be really what we need. So here's a truth table that it gave us. It said if P was true and Q is true, if P arrow Q is true. If P is true and Q is false, P arrow Q is false. If P is false and Q is true, P arrow Q is true. And if P and Q are both false, then P arrow Q is again true. So the trick to getting this to fit into our way of looking at expressions of logic now is to think of this arrow as a predicate. That is, we can think of P arrow Q as a variant, a different way of writing arrow applied to arguments P and Q, where the arrow is just like some other predicate. P is just like argument, a first argument, and Q is just like a second argument. Okay? And if we do that, then we're going to say the same thing that we say for all two-place predicates. If we have a two-place predicate that takes two arguments, it's true if and only if the ordered pair made up of the interpretation of the denotation of P followed by the denotation of Q is a member of the denotation of our predicate. So what is the denotation of our predicate, in this case, of our arrow? Well, it's going to be this. It's going to be the set that contains three ordered pairs. It's the three ordered pairs that give us true in the truth table. Namely, the pair TT, the pair FT, and the pair FF. Okay, so finally, we can go ahead and give our full analysis of this, of the denotation of the predicate logical formula. For all Z, if Z is a person, then laugh of Z. We say it's going to be true if and only if for every individual X, this, interpreted with respect to the instructions to interpret Z as X, is true. And since we now know what to do with our arrow, we can tell when this is going to be true. This is true if and only if the translation of this with respect to these instructions paired with the translation of this, laugh of Z, with respect to those same instructions is a member of the translation of arrow, again, with respect to those, those instructions. Okay, so that's written out here. Okay, and that will be true if and only if, I'll leave this part untouched, whatever we get out of this is a member of the denotation of the arrow, and the arrow doesn't contain any Z's, so its denotation will be just as it was before. It's a set of three pairs of truth values. The pair TT, the pair FT, the pair FF. Okay, so now let's take a look at what person of Z is when interpreted with respect to the instructions to assign to Z the individual X. That will be true if and only if the interpretation of the variable following those instructions is a member of the interpretation of person following those same instructions. The interpretation of the variable following those instructions is X. The interpretation of person following those instructions is the set of persons or set of people. We do the same thing for laugh. Laugh of Z interpreted with respect to the instructions to assign to Z the individual X comes out as true if and only if X is a member of a set of individuals that laugh. Okay. So now we have to consider 3 different cases. Case 1 is where X is a person and X laughs. In that case, whoever X is, this will denote that person X. This will be true because that person X is a person. I'm sorry. This will be true because that person X laughs. And so this will be 2 truth values, true here and true here. That'll give us the pairing true and true. A second case that is one of the allowed cases is this. X is a person, X is not a person, but X laughs. If X is not a person, this, which is true just in case X is a member of the set of people, will come out as false. If X is not a person, X is not a member of the set of people. But if X laughs, this will come out as true, so this will be the pair FT. Finally, case 3, if X is not a person and X does not laugh, we end up with person of Z with respect to the instructions to assign Z to X is false, and similarly for laugh of Z, assign interpreted with respect to the same instructions. Okay, so let's go ahead and check our situation and make sure that we got the right prediction. Our situation is there are 5 individuals, A, B, C, D, and E. A and B are people, C and D are monkeys, E is a pencil. A, B, and C all laugh. And we observed that the sentence, everyone laughs, is true. So here now is the full-fledged analysis going from the beginning to the end. We translate the sentence, everyone laughs, into the predicate logic formula for all Z, person of Z, arrow, laugh of Z. We give a denotation for that formula. It's true if and only if, for every individual X, person Z, arrow, laugh of Z is true. That's true if and only if, for every person, every individual X, the pair made up of person Z interpreted with respect to instructions to interpret Z as X, together with the interpretation of laugh of Z following the same instructions, is one of the 3 pairs of truth values that are the interpretation of arrow. So here's what we have to do. We have to check whether that's true for all of the individuals that we can put in this position and this position. So we check for person Z interpreted with respect to A for Z, and laugh of Z interpreted with respect to the same instructions, A for Z. This person Z, A for Z, I can't seem to just get that. No, is true just in case A is a person. Okay, it's set up here for any individual X, we check X, and back here, we saw that that's going to be true if and only if X is a person. Okay, we have to do it for every X, and now we have X equals A, so we have to check and see if A is a person. Okay, in our situation, A was a person, and A laughed. Since A was a person, that gave us a T for the first one. Since A laughs, that gives us a T for the second one. So this is this, which is a member of this set. So our first individual has passed the test. Okay, that's spelled out here in a little bit more detail. We check is person Z with respect to A for Z, laugh of Z with respect to A for Z. What does it equal? It equals TT. Okay. And the same is going to be true with B. Okay. Here I just did A, but we also have to check for B. We have to check for C in place of X. We have to check for D in place of X. We have to check with E in place of X. Okay, we have to check 5 different things. Okay, so our first one checked out, that was with A. The second one we check out with B, and we find that B is a person and B laughs. So interpreting Z as B gives us, again, the ordered pair true, true. Case C was our laughing monkey. Okay, laughing monkey is not a person. I can't get the C for Z in there. There we go. It is not a person. So that part is false. But our laughing monkey does laugh. That gives that part is true. Finally, we have our non-laughing monkey, and we have our pencil. Neither of them is a person. This part is false. This part is false. Neither of them laugh. This part is false. This part is false. So both of these end up giving us the pair FF. And we check, are all of those members of the set, which is the denotation of arrow? Answer, yes. TT is a member of that set. That shows up right here. FT is a member of that set. That's right here. FF is a member of that set. That's right here. And so for every individual X, that is for A, for B, for C, for D, and for E, this comes out as true. And therefore, our original formula for all Z, person Z, or arrow, laugh of Z is true. Now, if this looks a little bit complicated and hard to follow, it is. It took a mere matter of thousands of years before somebody came up with a systematic way of interpreting quantifiers that works for at least these quantifiers. But it at least works. Okay, so now we have a prediction that the sentence everyone laughs is true in the situation. We observe that it's true, and so our prediction matches our observation. Okay, we have one last thing we have to do, and that is to give a way of translating the word everyone. Right? We started off just by saying, suppose saying that the translation of the sentence everyone laughs is simply what I've given you here. But ultimately, we want that to come by combining the translation of everyone with the translation of laughs. And we know what the translation of laughs is. We've been assuming that all along. We'll keep that same assumption. And the question now is, what is the translation of everyone? We know its type. We calculated that already. Its type is ETT. That means it has to take an argument of type ET. That's here, lambda P, where P is of type ET. And it has to give back something that's true. This whole thing, whatever it is, has to be something that's either true or false, I should say. Okay? But we know more than that. We know that replacing this P with the interpretation of laughs, the translation of laughs, should ultimately give us the interpretation, the translation of everyone laughs. And so we can fill in what we need. Rather than just dot, 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 P dot, 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 we can give it this. This is basically everything we had up here with laugh changed into P. This is our instructions that say to put the interpretation of laugh into this position. And so it should work, but let's go ahead and step through it step by step and show that in fact it does work. Okay. Everyone laughs will be interpreted as everyone, the translation of everyone applied to the translation of laughs. We just said that this is the translation of everyone. This is the translation of laugh. And so we take that and we plug it in place of P. That is, we take that full function, lambda x sub e, laugh of x, and we substitute it in for P. That gives us a function that still has to apply to an argument. And this says, look for something that can play the role of x out here. When you find it, substitute it in place of x and give back the result. Okay. So that was the result we wanted. We wanted to get everyone laughs equals for all z, person z, arrow laugh of z. And we got everyone laughs equals for all z, person z, arrow laugh of z. Okay, the last thing I want to do in this chapter is shifting gears a little bit. It's looking at definite descriptions. Definite descriptions are kind of in between names and quantifiers. They have the form, that is the overt form of quantifiers. Just like you can say every professor, you can say the professor. You can say no male professor, you can say the male professor. You can say every student who is in this class, you can say the student who is in this class. That's not a very good use, that last one, because there is more than one student, but it's a perfectly fine expression. Except that these don't seem to act like quantifiers. They seem to act more like names, like picking out individuals. In this class, the professor is me. Or we can think of the following, a situation where we have a university class taught by Professor Mary Smith, a female professor, with 20 students registered for the class. In this case, we can use the expression, the professor, to pick out Professor Mary Smith. Now, something that's a very important property of definite descriptions is this. In the same situation, the expression the student doesn't seem to pick out anyone. And the reason is because we've used student in the singular, and the student is only going to pick out somebody if there's exactly one student around to be picked out. But in this case, there were 20 students. It's like the has to have things already pre-selected. It's not going to pick out one out of the 20. There has to only be one to pick out. And here you've given 20 options, and it just says, huh, I give up. I don't know what to do. So the student, we'll say, is undefined. We'll use this hash mark to say that it is not appropriate in this context. What about male professor? In the situation I've just given you, there is one professor, but it's a female professor. That is, there are no male professors. Well, then we can't say the male professor to pick someone out. This doesn't pick anybody out in that situation. Once again, it's inappropriate, and hence the hash mark at the beginning. Okay. So now we want an analysis that tells us exactly that. And we're going to do it by starting off with the notion of a presupposition. We're going to say that an expression of the form the phi presupposes that there is exactly one individual that phi is true of. If this presupposition is satisfied, then the phi denotes that unique individual that phi is true of. But if that presupposition is not satisfied, then the expression the phi does not denote anything. We say its denotation is undefined. And here's how we're going to do that. We're going to take the translation of the phi into logic to be this. Okay. This, we've translated the part, and we say put whatever the translation of phi is into here and give back the result iota x followed by that translation of phi. Okay, this iota is not a quantifier. I said it looks kind of like a quantifier. Its translation into logic looks very similar to the translations we gave to the quantifiers as well, but it's not a quantifier. It's not a quantifier because it denotes an individual. It denotes the unique individual having property phi. So let's spell that out formally. We're going to do it like this. The translates as instructions to find a one-place predicate P, like professor, for example, and give back iota x, P of x. Okay, so now let's show that that gives us something desirable. We'll try it out with the professor. The professor takes the translation of the applied to the translation of professor. And we said that the translation of the is here. That's just copying from the top line. And the translation of professor is exactly what we'd expect. It's lambda y, professor y. And now we have to do our lambda conversion. We take this, we put it in place of p here, and give back the result, which is this. This result contains a function, lambda y, professor of y, applied to an argument, x, and we need to now take that and do another lambda conversion. We take that x, we put it in place of y, we give back the result. That is, this whole thing now becomes this, and we end up with iota x, professor x. Now, we need to figure out how to interpret our iota expression. Okay, we wanted to pick out an individual, but we only wanted to pick out an individual in case that P is true of exactly one individual. Okay, so I'll put it this way. If the denotation of P is a set that contains exactly one element, Z, for some individual Z. It doesn't matter who, but that Z has to be an individual. Then this gives us the unique individual Z that is a member of the denotation of P. This otherwise means if this doesn't hold, if that's not the case, so if the denotation of P contains 2 individuals or 10 or 0, then iota x, P of x is undefined. Okay, so where P was professor, and our situation was what we described above, the professor is well defined. And it picks out the unique individual such as Z is a member of the denotation of professor. That individual is Professor Mary Smith. The student doesn't pick out anyone because student has a denotation that has 20 members in this situation. That is, its denotation does not just contain 1. There are 20 individuals in there, A, B, C, D, E, all the way up to whatever the 20th letter is. And so this is an otherwise case. The otherwise case, the student is undefined. Iota x, student of x, more properly, has an undefined denotation. And finally, if we use male professor in place of P, male professor has a denotation in this context that's empty. There's nothing that we can put in this place. We end up with a set of brackets with nothing in it. And that's not a singleton set. It's not a set with one member. And so we're again in the otherwise case. The male professor is undefined. Okay, that's it for this week. I will see you all again next week.